Good morning to one and all present over here. On behalf of Erode Sengunthar Engineering College, Perundurai, Tamil Nadu, under the AICTE PRERANA scheme for preparing SC/ST students for higher education class. See, this session it is useful for the GATE coaching class for SC/ST students. Myself, L.ANBARASU, Associate Professor, belongs to EEE Department, Erode Sengunthar Engineering College, Tamil Nadu. In this session, we have to discuss about the testing of transformer, open circuit test and short circuit test. Today's session, we have to discuss about the various types of losses available in the transformer and also efficiency in transformers. What are the conditions for maximum efficiency of a transformer? And finally, we have to discuss about the testing of transformers. First, losses in a transformer. Generally, there are two losses are available in the transformer. So one of the losses is core or iron losses. Another losses is copper losses. In this case, the transformer gas, there is no rotating losses. So that's why it produces more efficiency, maximum efficiency. So mostly 95 to 99% of efficiency will be produced in the transformer. First type of losses, core or iron losses. So this loss consists of hysteresis and eddy current losses, which occurs in the transformer core due to the alternating flux. The core or iron losses, this loss consists of hysteresis and eddy current loss, which occurs in the transformer core due to the alternating flux. These core losses can be determined by open circuit test. The open circuit test, which is used to determine the one of the losses, core or iron losses. The hysteresis losses, it is given by the KHB maximum 16 F into V watts. It is the formula for the hysteresis losses. KH, it is the constant parameter. B maximum flux density. F, it is the frequency of the supply. V, voltage applied to the transformer. So another subdivision losses, eddy current losses, that is PE equal to KE B maximum square F square T square V. KE is the constant, eddy current constant. B max flux density, frequency, then thickness of the iron, voltage applied to the transformer. Here the both above the losses, which depends upon the B maximum and frequency, which are almost constant. Hence, the core or iron losses are practically the same at the all load conditions. So we have to consider for the core or iron losses for no load to full load conditions, it is always constant one, because it depends upon only B maximum and frequency, which does not depend upon the voltage or current. The next losses, it is the copper losses. These losses occurs in both the primary and secondary winding due to their ohmic resistance. The copper losses, it occurs in the primary and secondary winding due to the ohmic resistance. So whatever the resistance present in the winding means it produces an copper losses. That is the I square R losses. These copper losses can be determined by short circuit test. So short circuit test it is used to determine the copper losses of the transformer. It is given by PC, that is the copper losses, that is equal to I1 square R1 plus I2 square R2. I1 square R1 it is the copper losses on primary winding. I2 square R2 it is the copper losses on secondary winding. For ideal case, I1 square R1 equal to I2 square R2. These copper losses varies as the square of the load current. Always copper losses vary as the square of the load current. So mostly 90% of the losses which occupies the total losses. So copper losses account for the about 90% of the total losses. The total losses of transformer which is cumulative addition of cumulative percentage of iron losses and copper losses. Here the 90% losses on the account of copper losses, only 10% of losses are behind the iron losses only. Here the summary of the copper losses and core losses. Here the core losses it is the always indicated in constant losses. Here copper losses it is the variable losses. It depends upon the load current. You have to increase the load value means automatically load current will be value will be varied. So it is called as an variable losses. The core losses does not change even as the load current changes. Always it constant for the all the load conditions. So that's why does not change even as the load current changes. But in this case, copper losses, it is proportional to the square of the load current. So whatever the increasing the load means, the load current value automatically increases. So it is proportional to square of the load current. It is also called as I square R losses. Then finally, the core losses it is proportional to the supply voltage and frequency, not depends upon the current, but it is proportional to supply voltage and frequency. But in this case of copper losses, it is proportional to square of the load current. Copper losses which occurs in the winding resistance, but core losses which occurs in the core. Copper losses it is dissipated as in the form of heat. But in case of core losses, it produce it is split out the heat in the iron core. So it is the summary of copper losses and core losses. The next one, efficiency. Generally efficiency which means the output power divided by input power. The ratio of output power in secondary winding to input power in primary winding. That is called as an efficiency of transformer. Based on the losses, we have to calculate or determine the efficiency of transformer. Here the full load iron losses equal to Pi. It is determined from open circuit test. Full load copper losses it is equal to Pc. That is it is determined from short circuit test. From open circuit test and short circuit test, we have to determine the iron losses and copper losses. The total losses of the transformer, it is the iron losses and copper losses. We have to add the two losses. That is the total losses of the transformer equal to Pi plus Pc. That is iron losses plus copper losses. So based on the losses, we have to determine the efficiency of the transformer at any power factor. Any power factor value means 0 to 1. That is 25% of load, 50% of load, 75% of load under full load conditions at any power factor. Full load efficiency, it is equal to full load VA into power factor divided by full load VA into power factor plus iron losses plus copper losses. It is the formula behind the efficiency of a transformer. The full load VA into power factor, it is the output power divided by full load VA into power factor, output power plus losses, total losses, iron losses plus copper losses. It is the formula for efficiency of the transformer, output power divided by output power plus losses. At any load conditions, conditions means 25%, 50%, 75% full load conditions, we have to calculate the losses and also efficiency of a transformer. It is a formula behind the at any load conditions, you have to determine the efficiency of a transformer. At any load conditions, that is x times of full load, the total losses will be PT, that is total losses equal to iron losses plus x square into copper losses, where x equal to fraction value 0 to 1. We have to substitute for 0 to 1. But iron loss is always constant for from no load to full load, but copper losses which depends upon the load current. So that's why x square into copper losses. Finally, efficiency at x load conditions, that is eta x equal to x into full load VA into power factor divided by x into full load VA into power factor plus iron losses plus x square PC. That is a variable copper losses. Output power divided by output power plus losses. But then only we have to mention for x square into PC. That is the any load conditions. Here this formula, the iron losses always remains the same at all the load conditions. But only we have to remainder for this formula. Then we have to calculate for the conditions for maximum efficiency. In transformer, how to determine the conditions for maximum efficiency. We know that we have to consider for the secondary parameters only. Output power equal to V2 I2 cos phi 2. Output power of the transformer, that is equal to V2 I2 cos phi 2. V2 means secondary voltage or load voltage. I2 equal to load current or secondary winding current. Cos phi 2 load power factor. If R02, it is the total resistance of the transformer which is referred to the secondary winding. R02 is the total resistance of the transformer which is referred to secondary side. Then copper losses. What is the copper losses? Total copper losses is equal to IT square into R02. That is the copper losses in secondary winding, IT square into R02. So IT equal to load current, R02 equal to total resistance of the transformer referred to secondary side. We know that total losses of the transformer Pi plus Pc, that is iron losses plus copper losses. Then we have to substitute for the efficiency formula. Efficiency eta equal to V2 I2 cos phi 2 whole divided by V2 I2 cos phi 2 plus Pi plus IT square into R naught 2. Then efficiency eta equal to V2 cos by 2 divided by V2 cos by 2 plus Pi by I2 plus I2 into R naught 2. From the numerator and denominator, the common parameter is I2 is available. We have to separate into the outside. From we can get the V2 cos by 2 divided by V2 cos by 2 plus Pi by I2 plus I2 into R naught 2. That is a common parameters for numerator and denominator equal to I2. Finally, we can get the last type. Then how to uh, produce our condition is created means differential equation is useful to the determine the condition for the maximum efficiency. The variable parameters is I2, di by di2 for the denominator equal to 0. That is the formula for conditions for maximum efficiency. You can substitute d by di2 into V2 cos by 2 plus Pi by I2 plus I2 into R naught 2. That is equal to 0. Uh, by applying the differential equation, we can get first equation V2 cos by 2 d by di2 of V2 cos by 2, that is the 0. Then d by di2 of Pi by I2, we can get minus Pi by I2 square plus d by di2 of I2 into R naught 2. So finally we can get only R naught 2. So write the final equation 0 minus Pi by I2 square plus R naught 2 equal to 0. Then Pi equal to I2 square into R naught 2. So what is meant by Pi? It is the iron losses. What is meant by I2 square into R naught 2? It is the copper losses. It is the final conditions for the maximum efficiency of transformer. That is iron losses equal to copper losses. When the transformer in a transformer, the iron losses equal to copper losses, that condition is applicable for the to produce the maximum efficiency. At what condition the transformer produce maximum efficiency means iron losses equal to copper losses. That conditions only the transformer produce maximum efficiency. Here, hence the efficiency of a transformer will be maximum when the copper loss is equal to iron losses. That is the conditions for the maximum efficiency. Hence, efficiency of your transformer will be maximum when copper losses are equal to iron losses. From above equation, we have to determine the load current also. That is load current I2 corresponding to the maximum efficiency is given by IT equal to square root of Pi by R naught 2. And output kVA corresponding to maximum efficiency. Another formula, output kVA corresponding to maximum efficiency. That is PC equal to copper losses at full load kVA. PC, which means copper losses at full load kVA. PA, it is the iron losses. X, fraction of full load kVA at which efficiency is maximum. X, it is the fraction value or fraction of full load kVA at which efficiency is maximum. The total copper losses equal to X square into PC. For maximum efficiency, we can apply for the conditions PA equal to X square into PC. So finally we can get the fraction of load, full load kVA at which efficiency is maximum. That is X equal to square root of Pi by PC. It is the formula for output kVA corresponding to maximum efficiency. Output kVA corresponding to maximum efficiency is equal to X into full load kVA. Output kVA corresponding to maximum efficiency is equal to full load kVA into square root of Pi by Pc. Say we have to note that the value of kVA at which the efficiency is maximum, it is independent of the power factor of the load. Here we can note that the value of kVA at which the efficiency is maximum, it is independent of power factor of the load. So next we have to discuss about the testing of transformer. One of the tests, that is the open circuit test and the short circuit test. The circuit constant efficiency voltage relation of transformer can be determined by two simple tests: equivalent circuit constant parameters, efficiency of a transformer, and voltage regulation of transformer. All the things which can be determined by only two tests, simple test, that is the open circuit test and short circuit test. So these two tests are very important for the transformer testing. First one, it is the open circuit test. Open circuit test means transformer which has two windings, primary winding and secondary winding. One of the winding kept at open, that is kept at another winding is supply, another winding which is given to the supply. We can conduct it in an experiment. It is called as an open circuit test. So basically, high voltage winding kept at open, low voltage winding is given to the supply side. From the diagram, high voltage winding which is kept at open conditions, low voltage winding is connected across the supply side. This is the basic procedure for open circuit test. This test is conducted to determine the R naught and X naught. It is the no load parameters R naught and X naught. First, we have to apply for the rated voltage, which is applied across the low voltage side, and high voltage side always kept it open. So rated voltage means based on the nameplate details, we have to apply for the rated voltage of the particular low voltage winding voltage. This rated voltage is applied on low voltage side. At the same time, high voltage side is kept it open, or any voltmeter is applied across these two terminals of the high voltage winding. At no load condition, the current taken by the transformer is 3 to 5% of full load current. At no load conditions, the current taken by the primary side, it is only in the form of 3 to 5% of full load current. So that I square R losses is negligible. We have to consider for the I square R losses is negligible. Why? Because means it takes only 3 to 5% of full load current only. So that's why we have to consider for the I square R losses. That is the copper losses is negligible in open circuit test. Only one losses are there. That losses is called as an iron losses or O losses, because we have to apply for the rated voltage on the low voltage side, and high voltage is kept it open. So that transformer which produce only iron losses. From that open circuit test, what are the data observed from the test means? So one is the supply voltage, that is the V naught, that is the no load voltage. No load current I naught, this is the ampere no load current. Iron losses, it is the no load power factor, no load power. So power W naught equal to V naught I naught cos phi naught. Cos phi naught equal to W naught divided by V0 into I0. IW equal to I0 into cos phi naught. IM equal to I0 into sin phi naught. R0 equal to Vn by IW and X0 equal to Vn by IM. Here W naught equal to no load power, V naught equal to no load voltage, I naught equal to no load current, cos phi naught equal to no load power factor. From that open circuit test, voltmeter, ammeter and wattmeters are available. The unknown data, it is the cos phi naught. So cos phi naught we have to left side taken into the left side, other parameters are taken into the right side. W naught equal W naught divided by V naught into I naught. We can substitute the parameters, we can determine the no load power factor value. Another no load parameters, that is the IW, it is the working component current. It is the formula for working component current IW equal to I naught into cos phi naught. Another no load current, that is the IM, it is the magnetizing current. It is used to produce the alternating flux in the iron core. Working component, it is the losses working component current or losses component current. IM equal to I naught into sin phi naught. Then finally we can determine the no load parameters R naught and X naught value. R naught equal to V1 by IW or V naught by IW. X naught equal to Vn by Im or V naught divided by Im. So finally we have to determine the no load parameters R naught and X naught value. So it is used to draw the equivalent circuit of transformer. So these data which is observed from the open circuit test. The next test is it is the short circuit test. The short circuit test, which means we have to short circuit the any one of the winding, so especially for low voltage winding, because we are by circulating the maximum current in the winding. So only options is low voltage is kept at short circuit. So by this diagram, so low voltage circuit is short circuited by means of thick copper wire or ammeter. High voltage side we have to given for the supply, but we cannot apply for the rated voltage. Only low voltage supply is applied across the high voltage side. That means rated current only applied across the high voltage winding, not rated voltage. In open circuit test, rated voltage is applied across the primary winding or low voltage winding. But in this case, short circuit test, rated current only applied across the high voltage winding. This test is conducted to determine the R02 and the X02 value. That is the total resistance of the winding referred to the secondary side, total reactance of the winding referred to secondary side. That is the R02 and the X02 value. Then low voltage side of the transformer which is short circuited and the test is conducted on high voltage side. That is the voltmeter, ammeter and the wattmeters are always connected in the high voltage side winding. The low voltage is applied on the high voltage side to circulate the rated current on both the windings. Power drawn during this test is considered as copper losses. Here only we have to given for the rated current only applied across the high voltage winding. So due to the rated current flow through the high voltage winding, it will produce the more copper losses in the windings, both the high voltage winding and the low voltage winding. So by means of wattmeter, we have to observe the power drawn during this test. It is considered as a copper losses only, not core losses. finally, the data observed from the test is given by the applied voltage equal to VSC, that is the short circuit voltage, short circuit current ISC, copper losses, that is a WSC. So by means of voltmeter, ammeter, and wattmeter, these three parameters are observed from the test. Then WSC equal to ISC square into R naught 2. This is the formula for copper losses. WSC, which is equal to ISC square into R naught 2. R naught 2 equal to WSC divided by ISC square. Z naught 2 equal to VSC by ISC. So by means of wattmeter and ammeter, two parameters are available. Only one parameters are not unknown parameters, that is R naught 2. That is R naught 2 equal to WSC by ISC square. From that R naught 2, we can determine further X naught 2 value also. We know that in case of AC circuit, Z equal to V by I, that is Z naught 2 equal to VSC by ISC. That is X naught 2 equal to Z naught square minus R naught square root of. So based on their open circuit test and short circuit test, we have to draw the equivalent circuit parameters of the transformer and also determine the efficiency and the voltage regulation of transformer. Here in this case, one problem, that is to obtain the equivalent circuit of a 200 voltage bar 400 voltage 50 Hz single phase transformer from the following test data. From the open circuit test, there are data are available. 200 voltage 0.7 ampere 70 watts is available on the low voltage side. Short circuit test 15 voltage 10 ampere 85 watts, it is conducted on high voltage side. Calculate the secondary voltage when delivering 5 kilowatt at 0.8 power factor lacking, the primary voltage being 200 voltage. In this problem, we have to determine the equivalent circuit of that single phase transformer and also secondary voltage when delivering the 5 kilowatt at 0.8 power factor lacking. The primary voltage is being 200 voltage. It is a single phase transformer. Okay, we know that from the open circuit test, what is the formula? P naught equal to V naught I naught cos pi naught. From the open circuit test, voltmeter reading, ammeter reading, and wattmeter readings are available. The unknown data is cos pi naught. We have to substitute for the cos pi naught equal to P naught by V naught into I naught. P naught equal to 70 watts divided by V naught equal to 200 voltage into I naught equal to 0.7. So finally we can get the no load power factor value cos pi naught equal to 0.5. Then we can convert the cos pi naught into sin pi naught. We can get 0.86. So IW equal to I naught into cos pi naught. It is the working common current formula. You can substitute no load current I naught equal to 0.7. No load power factor value 0.5. We can get the IW value, that is 0.35 ampere. Another formula, IM, magnetizing current IM equal to I naught into sin phi naught. You can substitute for the no load current I naught equal to 0.7, sin phi naught equal to 0.866. So we can get the magnetizing current IM equal to 0.606 ampere. Then no load parameters, R naught equal to V naught by IW. So V naught equal to 200 voltage. From that given data is available in the transformer. Then IW equal to 0.35. Then R naught equal to 571.4 ohm. Then X naught equal to V naught by IM, V naught equal to 200, IM equal to 0.606. Then X naught value equal to 330 ohm. So it is a data determined from the open circuit test. Then next is from short circuit test, short circuit power PSC equal to ISC square into R naught 2. So from that formula, ammeter reading and wattmeter readings are available. Unknown data is R naught 2. R naught 2 equal to PSC by ISC square. You can substitute PSC in terms of 85 watts, ISC square 10 square. We can get the R naught 2 value, that is a 0.85 ohm. Then another formula Z naught 2 equal to VSC divided by ISC. You can substitute VSC in terms of 15 voltage, ISC in terms of 10 ampere. We can get the Z naught 2 equal to 1.5 ohm. Then X naught 2 equal to square root of Z naught 2 square minus R naught 2 square. It is the formula for impedance, resistance and reactance. Combination of resistance, reactance and impedance formula. From that formula, we can determine the X naught 2 equal to square root of Z naught 2 square minus R naught 2 square. We can substitute for the Z naught 2 in terms of 1.5, R naught 2 in terms of 0.85. Finally, we can get the X naught 2 value, that is 1.235 ohm. So from the open circuit test and short circuit test, we can determine the R naught X naught value and the R naught 2 and the X naught 2 value. So from that parameters, we have to draw the equivalent circuit of single phase transformer. So equivalent circuit report to primary side means K equal to V2 by V1. That is a V2 equal to 400, V1 equal to 200. We can get the transformation ratio K equal to 2. We have to convert the primary side parameters. That is, refer to primary side means we have to convert all the parameters in secondary side equal to refer to primary side. So R naught to 1 equal to 0.85 divided by 2 square. You can get R naught 1 equal to 0.212 ohm. Then X naught 1 equal to 1.235 divided by 2 square. Same thing, equivalent circuit refer to secondary side means K equal to 2, R naught dash equal to 200 into 2 square, that is 800 ohm. X naught dash equal to 115.5 into 2 square. So finally we have to draw the equivalent circuit of transformer, either refer to primary side or secondary side. Another data is load KVA corresponding to 5 kilowatt. 5 kilowatt, we have to consider for the kilowatt into watts, 5000 rupee, 0.8 per quarter. It is the per quarter value, it is available in the problem given data. So 5000 rupee, 0.8, we can get the 6250 VA, volt ampere. So lower current I2 while delivering the 6250 VA is 6250 divided by 400 voltage, we can get the 15.625 ampere. This is a load current value 15.625 ampere. From that 6250 volt is a 6000 volt ampere divided by 400 voltage. The total voltage drop in secondary when it carries 15.625 ampere is, it is the formula I2 into R naught 2 cos phi 2 plus X naught 2 into sin phi 2. It is the formula in the voltage relation of transformer. We can substitute all the parameters available in the data. So 15.625 into 0.85 into 0.8 plus 1.235 into 0.6. We can get the voltage drop across the secondary winding. Voltage drop in secondary winding, it is equal to 22.020 voltage. Hence, the secondary voltage is V2. It is the available voltage is 400 voltage. We can subtract the drop voltage. Finally, we can get the secondary voltage VT equal to 377.8 voltage. It is the final answer for this problem. Okay, again, we have to refer for this problem. Uh, we have to given for the open circuit test value and the short circuit test value. Uh, First one case is we have to draw the equivalent circuit of the transformer. Then finally we have to determine the secondary voltage when 5 kilowatt at 0.8 power factor lacking, when the primary voltage being 200 voltage. From that open circuit test, we have to determine the R naught value and the X naught value. Available data is in the primary parameter side. And from a short circuit test, we can determine the R naught 2 value and the X naught 2 value. Then we get to draw the equivalent circuit of the transformer. Based on the value, finally we can determine the secondary voltage. Another problem, same open circuit test, short circuit test problem. Here the corrected instrument readings obtained from open circuit and the short circuit test on 10 kVA 450 bar 120 voltage 50 years transformer, which are open circuit test V1 equal to 120 voltage, primary current I1 equal to 4.2 ampere, primary power, that is W1 equal to 80 watts. V1, W1 and I1 were read the on the low voltage side. Then short circuit test V1 equal to 9.65 voltage, I1 equal to 22.2 ampere, W1 equal to 120 watts. With low voltage when is short circuited, compute equivalent circuit constant, efficiency and voltage regulation for 80% lacking gap power factor load, and the efficiency at off load and 80% lacking for power factor load. It is a formula for the open circuit test and the short circuit test. Here the solution for this problem, from that open circuit test, the primary is open, the secondary draws a no load current of 4.2 ampere. Since K equal to 120 voltage divided by 450, we can get the 4 per 15. That is a transformation ratio. Corresponding primary, no load primary current I naught equal to 4.2 into 4 by 15. We can get the 1.12 ampere. Uh, First case, we have to determine the equivalent circuit parameters. That is V1 I naught into cos phi naught equal to 80. We can get the cos phi naught equal to 0.159. The phi naught equal to cos inverse of 0.159. We can get the 80 degree, 80.9 degree. So convert the cos phi naught into sin phi naught equal to 0.987. Working common current IW equal to I naught into cos phi naught. We can substitute the no load current 1.12 into cos phi naught equal to 0.159. We can get the 0.178 ampere. Always working common and mandation current less than 1 ampere. But any problem. The mandation current I mu equal to 1.12 into 0.987. We can get the 1.1 ampere. So no load parameters R naught equal to V1 by IW. We can get the 2530 ohm, and the X naught equal to V1 by I mu. We can get the 409 ohm. So during the short circuit test, from that reading, instruments which have been placed in the primary side. Then Z01 equal to 9.65 divided by 22.2. We can get the 0.435 ohm. R01 equal to 120 divided by 22.2 square. We can get the 0.243 ohm. From the parameters, we can determine the x01 equal to square root of 0.435 square minus 0.243 square. We can get 0.361 ohm. So these things are we have to compute it for the equivalent circuit constants. The second one, it is the efficiency and the voltage relation for 80% lacking power factor load. It is the equivalent circuit diagram for the transformer. Now full load condition I1 equal to 10,000 divided by 450. You can get the 22.2 ampere. The 10 kVA, we have to 10 kVA into VA, 10,000 divided by voltage V. It is the primary voltage. So finally we can get the primary current I1 equal to 22.2 ampere. The drop voltage equal to 22.2 into 0.243 into zero point 0.8 plus 0.361 into zero point 0.6. We can get the drop voltage across the primary side, that is 9.2 voltage. Finally, we have to determine the regulation of the transformer. 9.2 into 100 divided by 450, we can get the 2.04 percentage. Then full load losses of the transformer, it is equal to 80 plus 120 watts. How it is obtained means 80, it is the wattmeter reading in open circuit test. 120, it is the wattmeter reading in short circuit test. That is full load losses equal to 80 plus 120, we can get the 200. The full load output equal to 10,000 VA into zero point 0.8, we can get the 8,000 watts, it is the output power. The efficiency equal to output power divided by input power. Finally, we can get the 0.9757 or 97.57 percentage. That is output power divided by input power or output power divided by output power plus losses. Here the efficiency value is above 95 percentage. Why? Because means it has no rotational losses, only iron losses and copper losses. The same thing, we have to calculate the efficiency of the transformer at half load conditions. So half load conditions, that iron losses are constant but copper losses are variable. Here iron losses equal to 80 watts, same wattmeter reading, but copper losses we have to determine for the half load conditions only. So how to calculate the half load means 1 by 2 square into 120. That is x square into full load copper losses. Here the x value equal to 0.5 or 1 by 2. That is half load conditions. The copper losses equal to only 30 watts. The total losses of the transformer equal to 110 watts. The output power equal to 5000 into zero point 0.8. That is the 4000 watts. The efficiency of the transformer equal to efficiency equal to 4000 divided by 4110. We can get the 0.9734 or 97.34 percentage. Then another test we have to conduct for the transformer polarity test. Here the additive polarity and the subtractive polarity circuit diagrams are available. Additive polarity and the subtractive polarity, which means VA plus VB, that is equal to VC. It is the additive polarity. Same thing, VC equal to VA minus VB means it is the subtractive polarity. So based on their connections, we have to determine the polarity of the transformer. Measure for the polarity of the transformer based on the two types, additive polarity and subtractive polarity. Here additive polarity, it is additive polarity. The voltage between the primary side and the secondary side will be sum of the both high voltage and the low voltage side. That is the VC equal to VA plus VB. Here the diagram, the primary side voltmeter it is VA, secondary side voltmeter it is the VB. The interconnection of primary and the secondary winding it is the voltage voltmeter it is the VC. Here VC equal to VA plus VB means it is the additive polarity test. But the same thing VC equal to VA minus VB it is the subtractor polarity. Here the subtractive polarity, the voltage between the primary side and the secondary side will be difference of both the high voltage and the low voltage. The previous case, it is a sum of both high voltage and low voltage, but subtractive polarity, it is a difference of both high voltage and low voltage. In case of subtractive polarity, VC equal to VA minus VB. That means it is a step-down transformer. VC equal to VB minus VA, it is a step-up transformer. But in case of additive polarity, it is for a small scale distribution transformer. Subtractive polarity it is used for large scale transformer. And next low testance single phase transformer. It is a circuit arrangement of low testance single phase transformer. Here the voltmeter, ammeter and wattmeters are connected in primary winding and secondary winding. From that wattmeter reading in primary winding and secondary winding, we got to determine for the efficiency of the transformer at different load conditions. This output power divided by input power, we can get the efficiency of transformer at 0 to 100% of load conditions. And also it is used to determine the relation of your transformer. Open circuit test, short circuit test already previous slides we have to discuss about the open circuit test and the short circuit test of single phase transformer. All day efficiency. All day efficiency. Ordinary or commercial efficiency of transformer, it is defined as ratio of output power divided by input power. But in case of commercial efficiency, output power divided by input power. But in case of distribution transformer, all the premises of distribution transformers are energized all the 24 hours in a day. But the secondary windings supply only little or no load during the major portions of the transformer. Okay. Here, constant losses occurs during the whole day, but copper losses occurs only when the transformer is loaded. The performance of such a transformer is judged on the basis of energy consumption during the whole day, that is 24 hours. So that's why it is known as all day efficiency or energy efficiency. It is only applicable for distribution transformer, not applicable for power transformer. So this type of all day efficiency is applicable only for distribution transformer. Here the definition for all day efficiency, it is the ratio of output power in kilowatt hour to the input power in kilowatt hour of a transformer over a 24-hour period. It is known as all day efficiency. In the design of such transformer, efforts should be made to reduce the iron losses which continuously occurs during the whole day. Here are the some problems for the practice all day efficiency problem. Subness test, it is used to dictate transformer. At a time, we have to determine for the efficiency of the transformer, or we have to conduct for the open circuit test and short circuit test at that time by means of connecting the two transformer connected in parallel. It is also known as subness test. Then separation of no losses in single phase transformer. Iron losses consist of hysteresis and eddy current losses. We have to separate the hysteresis losses and eddy current losses based on their base by conducting the separation of no losses on single phase transformer. It is a circuit arrangement for the separation of no losses. Here in this session, we have to discuss about the single phase transformer, various types of losses, efficiency of the transformer, then conditions for maximum efficiency, then testing of transformer, open circuit test and short circuit test, then corresponding problems, then finally load test and subnet test and all day efficiency of your transformer. So definitely in this session is useful for this SCST students for the preparation of GATE coaching class. The next class we have to discuss about the some other topics for the electrical machines. Okay, thank you.